Thus far in our unit on magnetism, we've talked about the source of all magnetism. That is, that in all cases, it's moving electric charges that give rise to magnetic fields. We've also talked about the effect of magnetic fields on matter, that whenever a charged particle moves in a region where a magnetic field exists, okay, it can experience a deflecting force. Okay, whether the charge is moving freely in space or if it is confined to a conducting wire. What we haven't talked about yet, okay, but we'll address today, is the form that these magnetic fields take. How can we predict the shape, okay, of the magnetic field around moving charges? Okay, remember that a magnetic field, like an electric field, okay, is a vector field. So we would need to describe both the magnitude of the magnetic field, okay, reflecting the strength of the field, as well as the direction of the field, okay, which also plays a part of the form of the field, okay, at every point in space surrounding a moving charge distribution. So that is what we're going to be focusing on today. Now, once Ørsted recognized that moving electric charges cause magnetic fields in 1820, it was only 1 month later that the French scientists Jean-Baptiste Biot and Biot-Savart arrived at a mathematical expression to predict the form of the magnetic field surrounding a current-carrying conductor. This expression is what we call the Biot-Savart Law. And like I said, the purpose of this law is to determine the form, that is both the magnitude and the direction of the magnetic field surrounding a current distribution. Very often this electric current is confined to a wire, but it doesn't have to be. Okay, we can talk about a collection of moving electric charges, okay, that are freely moving in space as well. I'm guessing that many of you have taken the SAT at some point in your life. And do you remember those really annoying SAT analogy questions? Like, I'll give you an example here. A bird is to a dinosaur as a human is to a blank. And then you'd have to select the correct answer. And you would select the answer ape in this case. Well, if you're familiar with those questions, let me ask you a more appropriate one for what we're discussing here today. See if you can get this one. Coulomb's law is to the electric field as the Biot-Savart law is to blank. Aha. Okay, if you said magnetic field, you would be correct. So what I want to do here is, on this side, we're going to make a comparison between how Coulomb's law can be used to describe the electric field, something we're very familiar with, okay, in our unit on electrostatics. We'll make the comparison to how the Biot-Savart law can be used to describe the magnetic field. Starting with the source of the field in each case, well, as you well know, okay, it's electric charges that give rise to electric fields, regardless of whether those electric charges are at rest or in motion. In all cases, okay, an electric charge will produce or give rise to an electric field. In the case of magnetism, however, you know that, okay, electric charges on their own, okay, do not produce magnetic fields. You've got to get those electric charges in motion. And when that happens, a moving electric charge, okay, or as we like to say, an electric current, will give rise to a magnetic field. Now, when we look at Coulomb, using Coulomb's law to describe the electric field, okay, you recall that for a continuous distribution of matter, what we did was to break up our charge distribution, which I'm showing you here in blue. Okay, we broke up our charge distribution into an infinite number of infinitesimal charge elements, dq, where usually we let each dq represent a point charge. And then we calculated the contribution that each little dq made to the field, okay, the electric field, okay, at the field point in question, what I'm calling P right here. And using Coulomb's law, we said, well, that infinitesimal contribution to the electric field, okay, went like K times, okay, the charge dq, that infinitesimal charge, divided by r squared, okay, times r hat, this unit vector that gave this field direction. Once we had done that, we came up with an expression for the infinitesimal contribution to the field for each dq, expressed in terms of a single integration variable. We could then sum up all of those field contributions to get the total field, okay, at the field point, which in the language of calculus amounted to taking the integral of dE. Well, okay, very similar concept here, not the same, but similar when we're calculating magnetic fields. We replace a charge distribution with the concept of a current distribution. So a current distribution, and I'll just show you here, if we consider charges moving in a confined region of space like a wire, okay, then we can talk about a small piece of that current, okay, which I will call okay, DI. Okay, if the current, which has a magnitude and direction, is represented by I, we will look at an infinitesimally small piece of that current, piece of the wire, and we will then calculate, using the Biot-Savart law, the infinitesimal contribution that this little small piece of the current makes to the field, the magnetic field, at the field point P. And here is the expression we come up with. I say we, this is what Biot and Savart did, okay, several hundred years ago. So it looks like this. The infinitesimal contribution that, okay, that small piece of the wire, that current, makes to the field, magnetic field here at point P, goes like mu naught, okay, this permeability constant divided by 4 pi, times IDS. ds we will see is this infinitesimal displacement vector defining the direction of the current, cross r hat. So you'll notice that r hat points, okay, from this current distribution to the field point, okay, in the same way that r hat pointed from this very small charge element dq to the field point. Okay, so our understanding of r hat is pretty much the same. Divided by r squared, we also see this inverse square law. Okay, what you notice here, though, is that we have the cross product of these two vectors here, ds and r hat. We'll get to that in a second. But just like in the case for the electric field, when we can calculate the infinitesimal contribution of all of these small current elements, okay, to the field at that point P, we can then sum up those infinitesimal contributions, which in the language of calculus amounts to taking the integral, okay, of all of these, okay, small contributions to the field to get the total field. So how is Coulomb's law used to describe the electric field similar to the Biot-Savart law used to describe the magnetic field? Well, there are some similarities, as I've alluded to. In the same way that for Coulomb's law, an infinitesimal charge element produces, okay, this infinitesimal field contribution dE, here we are saying that an infinitesimal current element produces this infinitesimal contribution to the field dB. We also notice that the magnitude of the field is inversely proportional to r squared. Okay, we have an inverse square law. That applies to the case of the electric field. It also applies to the case of the magnetic field. Okay, notice the 1 over r squared dependence in both of these laws. There are some important differences, however. In the case of Coulomb's law, okay, you will notice that the direction of the field is radial. It is in the plane, okay, the direction of the electric field is in the plane formed by dq and that field point P. Okay, whereas in the case of the magnetic field, we have this cross product, which tells us that the magnetic field, okay, the direction of the magnetic field will be perpendicular to the plane formed by both ds and r hat. Secondly, we notice that in real life, Okay, you can isolate a single point charge. Okay, it is possible to have a single point charge isolated in nature. Whereas when we talk about a current element, okay, that is a fictitious quantity. You cannot isolate a current element. This concept doesn't really exist, okay, but it is a useful concept to evaluating the total field. All right, so in this slide, we will talk about a four-step process for how to go about applying the Biot-Savart law to calculate the magnetic field surrounding some current distribution. So the first step in the process, okay, is going to be to break up the current distribution into an infinite number of infinitesimal current elements, di, okay, where each di, which is a vector here. I just want to point out, remember that for Coulomb's law, dq, each charge element, that was not a vector quantity, but now we're saying that this current element, okay, it not only has a magnitude, it also has a direction. And the magnitude of di, okay, is given by the current I. The direction of the current is given by this displacement vector ds, which defines the direction of the current, okay, for each of these little current elements. Once that is done, at the given point in space, that is the field point where we're trying to evaluate, okay, the field, we determine the direction of this differential magnetic field contribution dB, okay, and you notice when you look at the Biot-Savart law, okay, the direction of dB will be the direction of the cross product of these two vectors, ds and r hat. Remember, ds is infinitesimal displacement vector describing the direction of the current. R hat we described in the same way. We defined R hat when we applied Coulomb's law, okay, to figure out the electric field, right? R hat, the unit vector that went from the charge element dq, is directed from the charge element dq towards a field point. In the same way here, R hat is that unit vector that is directed from our current element towards a field point. Okay, so once the direction of the field is known by, okay, using the right-hand rule to figure out the direction of ds cross r hat, then we can focus on the magnitude of, okay, this differential contribution dB, okay, for each of the current elements, each of the di's that we have. And the magnitude of dB is found simply by applying the rule for the cross product of two vectors, right? When we look at the Biot-Savart law here, okay, I ds cross r hat means the magnitude would be given by I times the magnitude of ds, okay, times the magnitude of r hat, which is 1, the magnitude of any unit vector is 1, times the sine of the angle between ds and r hat. I just want to point out here that just as in the case of applying Coulomb's law to figure out the electric field, in order to evaluate the integral, we had to get a single integration variable. Same thing applies here. So all you learned, all these tricks you learned for being able to get that single integration variable, okay, will come in handy when with magnetic fields as well. So we need to get dB, okay, the magnitude of this infinitesimal field contribution here expressed in terms of a single integration variable. Once we do that, we can then take the vector sum of all the dBs, okay, by integrating over the entire current distribution and get the total field, okay, at our field point. All right, so now that we've developed this four-step process for applying the Biot-Savart law, we will now apply the Biot-Savart law and calculate the magnetic field for, okay, several current distributions. And we will start with the case of the magnetic field, okay, surrounding a long, straight, current-carrying wire. So let's get a picture of this. Here's our wire, which we will align with the y-axis. Okay, we assume that that wire is carrying a current I. And the first step in the process is to break up that current in the wire into an infinite number of infinitesimal current elements di. So here is one of our di's, which is equal to I times ds. Remember the vector ds, that displacement vector, defines the direction of the current at that point in question, okay, for that particular current element. And so there we have it. There's step one. Step two is to find the direction that this current element makes to the field, the contribution that it makes to the field dB. And we're talking only about direction here, not magnitude. So remember, the direction of this infinitesimal field contribution dB, will be in the direction of the cross product of ds and r hat. So we see what ds looks like. It's in the plane of the screen here. Okay, there's our field point. Remember that this r represents the distance between the current element and the field point, and that r hat, just as in the case for Coulomb's law, is a unit vector that is directed from, in the case of the electric field, it was directed from the charge element. In the case of the magnetic field, it's directed from the current element, to the field point. And like I said here, r, big R, will represent a constant distance, shortest distance between the wire and the field point. You'll see why we call it r in a second here. So in order to determine the direction of the magnetic field at the field point, we need to determine the direction of this cross product ds cross r hat. So when you take the fingers of your right hand, let them point along the first vector in the cross product ds, let them curl towards the second vector in the cross product r hat, and your thumb will point in the direction of the cross product, which, when you do it for this case here, remember the cross product is perpendicular to the plane formed by those two vectors. When you do it for this case, you see that the direction of the field, is into the plane of the paper at that point. Okay, so I want to point out something kind of important here. You remember that when we applied Coulomb's law, one of the problems, one of the sticking points was that the direction that each of the dq's made to the field dE, that direction very often changed with each dq. That made evaluation of the integral rather difficult. But you notice something kind of nice here, is that the direction of every dB, due to each of the current elements di, will be exactly the same. So imagine here, I'm showing you one particular current element here, but any current element you could look at along the wire, the direction of dB will be the same. And that makes the calculation here, rather easy. I want to point out here that what I'm showing you is what the magnetic field looks like at the single point P. But you can imagine here that when this two-dimensional picture is translated into 3 dimensions, so imagine taking your x-axis, and now we want to go into and out of the plane in, let's say, the z direction. Imagine taking this vector, which we said points into the plane of the paper, and now imagine rotating that vector through 360 degrees around the wire so that we get the z direction as well. What you will notice is that the direction of that field will completely encircle the current source. It will completely encircle the wire. So for the case of the straight wire, these field lines form concentric circles about the wire. And you have to, I would say this is what makes magnetism a little bit tough, is you have to be able to think in 3 dimensions. So I'm saying that the magnetic field at this one field point P goes into the plane of the paper, but imagine doing that for lots of different field points, and you will see that when we take a 2-dimensional picture and translate it into the 3-dimensional realm, that these magnetic field lines will encircle their current sources. And in the case of the straight wire, okay, due to the cylindrical symmetry here of the wire itself and the current distribution, okay, then we will get concentric circles. So we actually have another right-hand rule, one of the many right-hand rules that we will now introduce to determine the direction of the magnetic field lines. So here is how we state the rule. When you place the thumb of your right hand, okay, in the direction of the conventional current, you will notice that your fingers, okay, and if you think about the case of this wire here, okay, your fingers will encircle the wire. Okay, your fingers will naturally curl around the wire in the direction of the magnetic field lines. So, remembering that magnetic field lines encircle their sources, letting your thumb point in the direction of the conventional current, your fingers will now curl naturally in the direction of the magnetic field, okay, in order to encircle their current sources. So we can show this with, okay, this visualization here. Okay, so notice here the right hand, and notice the direction of the current. Notice the thumb is in the direction of current, and notice that the direction of the magnetic field lines, okay, will be the direction that the fingers of the right hand curl around that wire.
So now we're going to take a look at magnetic field patterns surrounding current carrying wires. So in the first case we're going to look at this straight wire which is coming into and out of this plexiglass plane. And what I've done, rather than use iron filings, I've placed some compasses around this wire. And notice right now there's no current in the wire, so these compasses point in a north-south direction, in this direction. In a second I'm going to turn on the power supply. We're going to get a large current through the wire, and you're going to notice that these compasses will align themselves with the magnetic field produced by the current carrying wire. So here goes. On the count of three, take a look at the compasses and we'll see what happens. Okay, if you'll notice here, these compasses show the direction of the magnetic field lines. And you see how if I take my pen and trace around them, they form a circular ring around this wire. This is characteristic of the magnetic field pattern around a current carrying wire. The magnetic field lines form concentric circles.
All right, so now that we've established the direction of the magnetic field surrounding this current distribution, right, and we can say it's generally true regardless of that current distribution that all magnetic field lines will encircle their sources. Okay, in the case of the straight wire, where that wire is a right circular cylinder, then these magnetic field lines are circular themselves. So now that we know the direction of the field lines, we can focus on the magnitude, okay, of this infinitesimal field element dB. And the magnitude is given by the Biot-Savart Law. So, as we've said before here, okay, the goal is to, be able to get a single integration variable. So I want to point out here, notice the angle theta, right? That is the angle between ds, the vector ds, and the vector r hat. And when we take the cross product of ds and r hat, we end up with the magnitude of ds here times the magnitude of r hat, which is just 1. It's a unit vector, times the sine of the angle between them. So we've got to get a single integration variable. If you notice here, okay, when we look at this expression, okay, for dB, Biot-Savart Law gives us IDS sine theta over r squared, okay, times this constant mu naught over 4 pi. Well, we will let ds, the magnitude of ds, become dy, since it is a displacement in the y direction. So just making that substitution there. When you look at this expression, you'll notice there's really 3 variables, right? We've got r, theta, and y. So we've got to somehow use a little bit of trigonometry, be creative, and get those 3 variables into 1. Well, that's not too hard, as we're going to see here. Okay, so r theta and y we can express in terms of a single integration variable y. How do we do that? Well, okay, notice this right triangle right here. Notice that r squared, this variable, is simply equal to, okay, big R, which is a constant. That's the distance between the field point and the center of the wire. Okay, big R squared plus y squared. Well, now we've at least, okay, expressed r in terms of y, so we've gone from 3 variables down to 2. Okay, next we take a look at the sine theta factor. And you'll notice here that the sine of this angle theta here is the sine of its supplement. It's a sine of 180 minus theta, what I'm showing you with my laser pointer right here. So again, when we look at this right triangle here, and we look at the sine of this angle right here, okay, which by definition is the opposite side of the right triangle over the hypotenuse, okay, which is going to be big R over the hypotenuse R, which we already said is just square root of r squared plus y squared. So here we have it, okay, with those two expressions here, we now can write this expression for dv in terms of a single integration variable. And it's going to look like this, right? Okay, we've got mu naught over 4 pi I, okay, times dy. Okay, remember r squared in the denominator becomes r squared plus y squared down here. And when this expression sine theta becomes big R over the square root of r squared plus y squared. So that gives us the factor r here, and it raises our exponent from a squared to a 1.5 or 3/2 power. So given this, we have succeeded in writing the magnitude of the field, okay, at our field point here in terms of a single integration variable y. So in the next slide, we will complete the process and do the integration. All right, so now that we know the direction of the field and we have an expression for the magnitude of dB, okay, expressed in terms of a single integration variable, all that's left to do is to perform the integral to basically sum up all of these infinitesimal field contributions, okay, due to all these current elements di. And as I said, this amounts to taking the integral over the limits of the current distribution. So here, this is what we're left with here. We can take all the constants outside of the integral, and we're left with the integral of, okay, this expression r squared plus y squared to the negative 3/2 power times dy. If this is an infinitely long wire, then we will assume that our current distribution in the y direction goes from negative infinity to positive infinity. And in order to evaluate this integral, this is not a simple integral, a simple polynomial integral in the form of u to the n du. Okay, so this is one where using a table of integrals or, okay, the internet would be a good idea. Okay, this is one of those special cases here. So when we look at this, we look it up. Okay, this is how we evaluate this integral. When we apply it to our particular problem here, we come up with this for an answer here. So we notice that the limits of the integration here from negative infinity to infinity, okay, and we will run through this really quickly here. Okay, when we plug that in here, just notice that, okay, starting with our upper limit of positive infinity, we get positive infinity divided by the square root of, well, okay, we can ignore the r squared factor compared to infinity squared. Square root of positive infinity squared is just infinity, so we get infinity over infinity. Okay, minus, when we plug in our lower limit of integration of negative infinity, well, the numerator becomes negative infinity, okay, but the denominator remains the same because we're squaring the negative infinity and then taking the square root. So we end up with here, you know, infinity over infinity is 1 minus negative infinity over infinity is negative 1. Okay, we do the number crunching, and 1 minus a negative 1 is 2. Very important result here. That's why I'm, okay, putting it with this yellow background here, you want to memorize that. Okay, so for a long straight wire, the magnetic field strength goes mu naught I divided by 2 pi r. I being the current, r being the distance you are away from the wire. So I want to point out a couple things here. And I'll remind you, when we looked at the electric field surrounding a charge distribution that had the same symmetry, okay, the symmetry of a right circular cylinder, okay, replacing charge with current. Remember what we learned, okay? And I'll put up here the expression. When we applied Gauss's law for electricity and we found the form of the electric field for a cylindrical charge distribution, this is what we came up with. So look at the similarities here. First of all, you will notice that, okay, the electric field was directly proportional to the charge distribution, okay, lambda, okay, the charge density, sorry, lambda, for that right circular cylinder of charge, in the same way that the magnetic field, okay, is directly proportional to the current in the, okay, right circular cylindrical wire. Okay, so we've got that in common. You'll also notice the inverse, the relationship to the distance of the field point from the current distribution or charge distribution, okay, whether we're talking about the electric or magnetic field. Notice that inverse relationship. The electric field goes like 1 over r, in the same way the magnetic field gets weaker as, okay, distance goes like 1 over r. So, you know, there's a lot of talk in the last couple decades about, you know, the effect of magnetic fields on the human body. And this is something to keep in mind, okay? Notice that there's that inverse relationship, right? So the further away you get from the source of the magnetic field, that is your current carrying wire, okay, the weaker that magnetic field gets. So that inverse relationship tells you that, you know, you don't have to get too far away for that field to get extremely weak, okay, according to that inverse relationship with distance. We'll apply the Biot-Savart law using the same series of steps to a different example here. So we're looking at 1/4 of a circular loop, okay, that carries a current I. And you'll notice from the diagram that the current enters the loop along the y-axis in the negative y direction and exits, okay, the loop along the x-axis in the positive x direction. We're asked to find the magnetic field, okay, that would mean the direction as well as the magnitude at the center of this quarter circle, okay, really at the origin of this coordinate system here, which I label C. So, okay, the first step is to break up the current distribution into an infinite number of infinitesimal current elements di. And we see here that really there's 3 different pieces or segments to this current carrying wire loop. So I'm going to call this segment aligned with the y-axis here, I'll call that segment 1. Okay, let's show our little infinitesimal current element di there. And you will notice that the displacement vector ds, okay, is in the negative y direction. So we will describe that displacement vector as minus dy times j hat. Now for the curved portion of this wire loop here, that's what I'm going to call segment 2. Okay, let's look at our infinitesimal, okay, current element there, di. And for this portion here, when we describe the displacement vector ds, okay, you will notice that okay, ds is in the negative theta hat direction. You recall in your course on mechanics, we introduced this unit vector theta hat, okay, and we said that by convention, positive values of theta hat would be tangent to the circle, but pointing in a counterclockwise direction. So because this current is traveling in a clockwise direction, that's where the minus sign comes from. And you can see here that using this concept of arc length, this infinitesimal magnitude of this vector ds here, okay, which I'll show you, we can describe as r, okay, the radius of that circle times d theta. And in this way, okay, at least we have everything expressed in terms of okay, the variable theta. Segment 3, this is the other straight portion here, and we'll show you the infinitesimal current element there. Okay, you'll notice that the displacement vector ds is along the x-axis in the positive x direction, so we'll describe that as positive dx times I hat. All right, so with these displacement vectors defined, okay, we are now ready to determine the direction of the differential magnetic field contribution at the point C. Okay, and remember that the direction of the magnetic field will be in the direction of the cross product of ds and r hat. Well, now here we have really 3 segments, so we've got to consider, okay, the field contribution due to each of those segments. Okay, but here's where something nice happens. Okay, well, let me show you the r hat vector for each of these segments. So for segment 1, remember r hat is that unit vector that goes, okay, from the current element to the field point. So for segment 1, it, okay, will look like, okay, what I'm describing here. Okay, it will be in the negative y direction. For segment 2, okay, it's going to be in the radial direction, but pointing towards the center of the circle. And for segment 3, that unit vector will be in the negative x direction. So you'll notice here that when we take the cross product for the straight portions of this wire here, okay, you know that the angle between, okay, the 2 vectors, that is ds and r hat, will either be 0, as in the case of this top current segment, okay, in which case there is no contribution, okay, to the field because of the, okay, directions here, okay, because ds cross r hat is 0. And similarly for this other straight portion here, you'll notice that ds and r hat are anti-parallel, and similarly we can reason that the sine of 180 degrees is 0 as well. So it turns out that only segment 2 makes a contribution to the magnetic field. And when you look at, you know, ds cross r hat using the right-hand rule here, okay, you should do this and convince yourself that the direction of that field contribution would be going into the plane of the paper at the field point C, okay, when you use your right-hand cross product rule. All right, so now that we know the direction of the field would be into the plane of the paper, okay, we can now, okay, which I'm showing you here, we can now work on the expression for the magnitude of that differential magnetic field vector here. And remember, only segment 2 makes a contribution. Okay, segments 1 and 3 don't make any contribution. So looking at segment 2, okay, looking at this expression here, you'll notice here that, okay, IDS sine theta, that there's a 90-degree angle between, okay, ds and r hat. And when you look at the magnitude, we're looking at the magnitude of ds times the magnitude of r hat, which is just 1, times the sine of 90. And you'll also notice here that, okay, mu naught over 4 pi, constants, I constant, r squared, you'll notice that r is a constant as well. Okay, that is just the radius of this quarter turn loop. So the only variable in this expression here is really ds, in which case we have a single integration variable, and we can now, okay, conduct the integration to evaluate the integral. And when we do so, okay, we see that pretty much everything comes out of the integral because they're constants, and we simply take the integral of ds over the entire current distribution, which is a quarter loop. So the integral of ds is just a quarter the circumference of the circle of radius r, which I'm going to write as 2 pi r over 4. And when we do the simplification here, okay, we end up with this expression mu naught times the current divided by 8 times the radius. So this is okay, what the total magnetic field will look like due to this quarter segment of current carrying wire. All right, so this last example we'll take a look at today, applying the Biot-Savart law, is a very important example because it tells us the magnetic field for a circular current carrying loop, and a single loop we will see is the basis for multiple loops, which we call a solenoid, to develop very powerful magnetic fields. So this is an important problem, and like I'm saying, one of the things that makes magnetism tough is that you have to be able to see or at least imagine in a three-dimensional world. So what I'm showing you in the figure here, this loop, is actually perpendicular to the plane of the screen here, and you kind of have to imagine that. So let's take a look here at applying the steps in the Biot-Savart law. We're going to break up our current distribution into an infinite number of infinitesimal current elements, di, and I'm showing you just a couple of these. I'm showing you a current element right at the top of the screen. What you're looking at in the screen is half of this loop. So you're seeing current coming out at you at the top. Okay, and what I can't show you is the current that continues through the other half of the loop and then will be going into the page, down here at the bottom. So you have to kind of imagine that. We're asked to find the magnetic field along the axis here. Okay, this is an axis of symmetry, what I'll call the x-axis here for this current carrying circular wire loop. So you'll notice here, as I say in the diagram, the ds, this displacement vector, the current is moving directly out of the plane of the paper right at the top, and down at the bottom, as we said, the vector ds is moving straight into the plane of the paper. So keeping that in mind, we're now going to determine the direction of the magnetic field, at our field point, which is going to be somewhere along the axis of this circular loop here, somewhere along the x-axis. And as always, to determine the direction of the field, we have to look at the cross product of these two vectors, ds and r hat. So when you notice here, for these two current elements I'm showing you here, when we look at the top, let's draw in the direction of r hat. Right? R hat always goes from the current element to the field point. And when I look at ds cross r hat, and make sure you do this and understand it, to get the direction, applying the right-hand cross product rule, that is, letting the fingers of your right hand lie along the vector ds and curl towards the second vector r hat, you will see that the direction of the infinitesimal field contribution dB would look like this. Notice that this vector dB is perpendicular to both r hat and to the vector ds. It's coming out of the plane of the paper. Likewise, when I look at the direction of the field contribution for the segment di down at the bottom of the screen here, again, I'm showing you r hat. You need to apply the right-hand rule, and you should notice that when you do so, the vector dB is going to look like this. Again, notice that dB will be perpendicular to both r hat as well as ds, that vector that goes straight into the plane of the paper. So what you can notice here with these two current elements, you can imagine in the third dimension, which I'm not showing you in the plane of the paper here, let's call it the z direction here, you can imagine that write it up here on the screen, that due to the symmetry that each di, and I'm showing you two di's, that for any di there will be another current element 180 degrees out of phase with it, that will give rise to a field, infinitesimal field dB, where the y and z components will cancel. So for example, these two di's I'm showing you here, you will notice that the y component of the dBs will cancel out, and for these particular choices there is no z component. in which case the only components that remain will be the X components. Okay, so you have to be able to kind of imagine this and reason then that all Y and Z components, okay, will cancel out due to the symmetry. So the end result is that okay, dB, the direction of it is going to be in the X direction, the I hat direction, and only the component along that axis is going to remain. So we can say that, okay, the direction of dB will be in the X direction, and it will have a magnitude given by dB cosine phi, okay, where phi, I'm showing you in the figure, is the angle that this infinitesimal field contribution makes with respect to the x-axis. Okay, given that, we can now calculate the magnitude of this, the field contribution here for each current element di. So for any current element, we say only the x component remains. Okay, y and z components cancel. So when we look at this expression for the Biot-Savart law here, okay, we can write it as follows. Okay, mu naught over 4 pi times the current, okay, times ds sine of 90. Okay, you will notice that, okay, like we said, the angle between ds and r hat is always going to be 90 degrees. We have the cosine of phi to get the component of dB, okay, divided by r squared, r being the distance between any current element and the field point. So you'll notice here we do have multiple variables, right? Let's take a look here. You will notice that r here, the distance between the current element and the field point, can be expressed in terms of constants, right? The radius of this current carrying loop, big R, is constant, as well as the field point we're looking at here along the x-axis. So really, R is a constant as well. Cosine phi here, okay, we can write, when I look at this right triangle here, notice cosine phi, adjacent side over hypotenuse. Adjacent side is going to be R over that big R, hypotenuse, little r. So we can express the cosine of phi in terms of these constants as well. So really, what we saw in the last case, is that okay, the only integration variable we really have, okay, is going to be ds. So making these substitutions here, cosine phi is equal to, big R over little r, and this is where we end up with our expression for the magnitude of, okay, the field contribution due to any current element di. So we'll finish this up on the next slide. All right, so all that is left to do here is to now, okay, integrate. That is, take the vector sum of all of the dBs, okay, the infinitesimal field contributions to each little infinitesimal current segment. And as I said, it's particularly simple because the only variable here is ds. And okay, x, little r, big R, all constants here, current constant, so it can be taken outside of the integral. So basically, when we take the integral of ds, okay, we sum up all these displacement vectors here. Okay, notice that we're talking about magnitude only here. Well, the wire is a circular wire loop. So when we sum up all of these, the magnitudes of these displacement vectors, we simply get the circumference of the circle of radius big R, okay, which is just 2 pi r. And when we simplify, okay, our expression looks like this. Now I want to point out something very important here, okay, and that is to make a comparison between the straight wire and the loop of wire. In other words, what is the effect on the magnetic field of taking a straight wire and bending it into a circular loop? Let's start by taking a look at what happens right at the interior of the loop as we let x go to 0. Okay, as x goes to 0, so that our field point, okay, becomes this point right here, okay, right in the plane of the loop itself, but right at the center of the loop. Notice that the magnitude of the field can be expressed as mu naught times I over 2r. Okay, well, let's compare that to the magnitude of the magnetic field for the straight wire. And you will notice that, okay, for the straight wire, the magnetic field at a distance r away was mu naught I over 2 pi r. So do you see here the effect? Okay, when we make a comparison, mu naught I over 2 pi r for the straight wire versus mu naught I over 2r, okay, for the loop, do you see that the overall effect by bending that straight wire into a loop, okay, is to increase the magnetic field by a factor of pi. Okay, in other words, the magnetic field at the center of the loop is 3.14 times bigger, okay, than the magnetic field at the same distance away from a straight wire, okay, at a distance r away for a straight wire. So this is significant because this is how we can develop very strong magnetic fields. Okay, when we take a single loop, we end up with a stronger magnetic field than a straight wire. Every time we will increase the number of turns, okay, in other words, by having two loops, we get twice the magnetic field strength of a single loop. So how are solenoids and very powerful motors produced? Simply by having a lot of turns or windings in your coil. A coil of wire is a way of producing an extremely strong magnetic field, okay, in the interior region of the coil. And we'll try to demonstrate this okay, on an upcoming slide.
We're now going to take a look at the magnetic field lines set up inside a current carrying loop. Now you recall that for the straight current carrying conductor, we saw that the magnetic field formed concentric circles around that conductor. If we take that straight conductor and now bend it into a loop, we see that those magnetic field lines get crowded in the interior of the loop, suggesting that the magnetic field in that region is quite strong. So notice with our loop here, we have our compasses aligned with the external magnetic field of the Earth because we have no current in the coil, in the loop yet. But once I turn on the power supply and create a current inside that loop, notice the compass in the interior of the loop, it will react quite strongly to that very strong magnetic field there. So let me turn on the power supply, and here goes. Okay, we see how intense the magnetic field is on the interior of that loop compared with the magnetic field on the exterior of the loop. In this demonstration, we're going to compare the magnetic field created by a straight current carrying wire, okay, to the magnetic field that you would get at the interior, the center of a current carrying loop. Now remember, we said that the effect of taking a straight wire and to bend it into a loop, okay, one that carries a current that is to crowd the magnetic field lines in the interior of the loop. And we showed that in theory, using the Biot-Savart Law, that when you take that straight wire and you bend it into a loop of radius r, that the magnetic field a radius r away from the straight wire gets increased by a factor of pi, 3.14, okay, once you bend that wire into a loop. Okay, in other words, the magnetic field at the interior of the loop, at the center of the loop, should be 3.14 times as big, okay, as the magnetic field the distance r away for the straight wire. So what you see here is you see a current carrying straight wire. Okay, I've got our power supply on, and I've got a magnetic field sensor, and we are going to, I've kept this loop here just so we can see the radius of it, and we're going to measure the magnetic field at the loop radius r away from the current carrying wire. So here it looks like we have a magnetic field of about 0.05 milliteslas, okay, due to that straight current carrying wire. Now we're going to measure the magnetic field at the interior of the current carrying loop. So let me turn on the power supply and generate a current here. Okay, and we see that it is about 0.16, okay, about 0.16 millitesla, which when you do your calculation, okay, 0.05 times 3.14 does give you a value of about 0.16 millitesla. So it looks like the theory using the Biot-Savart law works.
Now that we know both the magnitude and direction of the magnetic field surrounding a long, straight, current-carrying wire, we can look at a related but slightly different problem here, and that is, okay, the force that acts on two parallel current-carrying conducting wires. So here in the diagram, I'm showing you two wires. Okay, we'll imagine they're very long, and they are parallel to one another. And if we try to explain, what is it that will cause a force on these two wires? Well, let's take a look at the physics here. So what we can say is that a current-carrying wire in a magnetic field, we know experiences this magnetic force given by this expression IL cross B. So this is kind of a breakdown for what's happening here. We can say that the current in wire 1, let me show you that current, so we'll assume it's upward in this figure. And remember, okay, that current in wire 1 creates a magnetic field, we'll say B1, around wire 1. These magnetic field lines are concentric circles, and the direction of the field is given by, okay, one of these other right-hand rules, right? That is, you let, okay, the thumb of your right hand point in the direction of the conventional current, and your fingers will naturally curl around the wire in the direction of these field lines. So when I do that, okay, we see that the field lines are concentric circles. Now, I'm not showing you the direction yet, but what we can say is that the current in wire 1 creates a magnetic field B1 around wire 1, and likewise, okay, the current in wire 2, and I'm just, in this case, we'll assume that the currents are in the same direction. The current in wire 2 interacts with the magnetic field, okay, that is established by wire 1. So it interacts with B1. When you use you apply the right-hand rule here to determine the direction of the magnetic field. That is, okay, when you place the fingers of the thumb of your right hand along wire 1 in the direction of the current, you should notice that, okay, over where wire 2 is, the field should be going into the plane of the paper at that point. Okay, so knowing the direction of the field at wire 2, knowing the direction of the current in wire 2, we can now describe the magnetic force on wire 2 using the right-hand cross product rule. It would be this. Okay, so you're going to have to, make sure you apply these two right-hand rules here to see that this would be the direction of the magnetic force when you apply the rule IL cross B. Similarly, we can say that, well, wire 2 creates a magnetic field around it, okay, due to the current in wire 2. That current in wire 2 creates a magnetic field, we'll say B2 around wire 2, and that magnetic field will interact with wire 1 and exert a force on it. So let's show these magnetic field lines. Once again, applying the right-hand, okay, rule for magnetic field lines, letting the thumb of your right hand point along the direction of the conventional current in wire 2, you should see that over at wire 1, okay, the magnetic field would be coming directly out of the plane of the paper at that point. So, okay, wire 1, current carrying wire in a magnetic field, it too will experience this deflection force, okay, given by the cross product IL cross B. And you should see when you apply the right-hand rule there that it gives you a force vector that is, okay, pointing towards the other wire. So bottom line here, when we talk about the direction of these forces, we see that, okay, when the currents are in the same direction, okay, that the force on each of these wires we can classify as an attractive force. Well, what would happen if the currents are in opposite directions? Okay, let's quickly look at that case here. So for wire 1, we'll say the current is downwards, and in wire 2, it's upwards. Okay, going through the same reasoning here, okay, we can say, well, okay, the magnetic field created by wire 1 when it interacts with wire 2, okay, is going to be in this direction, coming out of the plane of the paper. When you apply the, okay, cross product rule for forces here, IL cross B, okay, you should see that in this case now the force, okay, on wire 2 is repulsive. Okay, it's directed away from wire 1. Similarly, when we look at the force on wire 1 due to the field created by wire 2, okay, we see that the field created by wire 2, okay, at the point in space of wire 1 will be coming out of the plane of the paper. And when you apply the right-hand cross product rule here, you see that this too gives you a repulsive force F1. So what we find out is that when the currents are in the same direction, these wires attract each other, but when the currents are in opposite directions, these wires repel each other. So just, okay, a little note from our, okay, friendly one-eared rabbit here tells us that, hey, whatever you learn in your psychology class about opposites attracting, it may work quite well when you're talking about people, when you talk about electric charges, even when you talk about magnetic poles, but it doesn't apply to current carrying wires, as you can see in this diagram. Now that we know the direction of, okay, the magnetic forces on these current carrying wires, we can derive an expression for the magnitude of the either attractive force or repulsive force on these current carrying wires. Now we can say that regardless of the directions of the currents, regardless of whether the force is attractive or repulsive, whether the currents are in the same direction or opposite directions, the magnitudes of these forces should be exactly the same, so long as the magnitudes of the currents are the same and the distance between the two wires is the same. So we will just arbitrarily take a look. We'll consider the case where the currents are in the same direction, like the top picture here. And as we said, okay, we need to start by knowing what the magnetic field looks like, okay, for each of these wires. And of course, the magnetic field, we derived the expression previously, mu naught I over 2 pi r, I being the current, r being the radius, okay, the distance away from the wire where we are evaluating the field. So since we placed the other wire a distance little d away from the first wire, okay, the distance we're looking at is little d. And so hopefully it makes sense to you that for wire 1, it produces a magnetic field around it, okay, due to the current in it. So it'll be mu naught I1 over 2 pi, okay, d. That is where the magnetic field of wire 1 interacts with wire 2. And likewise, for wire 2, it creates a magnetic field that depends upon the current in it, so we'll use I2. And again, we're interested in the strength of the magnetic field produced by wire 2 over at the position of wire 1, which once again is a distance d away. So given this, we can now take a look at the magnitude of the force, okay, from our cross product expression, right? ILB sine theta. So in this case here, the force on wire 1 will be equal to the current in wire 1 times the length of wire 1 times the magnetic field, which is due to the other wire, okay, times B2, the magnetic field due to the other wire at wire 1. Okay, and here you will notice that we're talking about the sine of 90 degrees, okay, being the angle between L, okay, which is the direction of the wire, and B, the direction of the magnetic field, which will be perpendicular to the plane of the wire. So we've got the sine 90 degrees. We can now just substitute in our expression for the magnetic field B2, okay, above here, substitute that in, and we can simplify, And we get this expression that the magnitude of the force on wire 1, okay, due to the magnetic field created by wire 2, it just goes like mu naught times the product of the currents times the length of the wire divided by, okay, 2 pi times the separation distance. Similarly for wire 2, okay, here's an expression for the magnitude of the force on it. Remember, the magnitude of the force on it has to do with the magnetic field of the other wire, wire 1. So we substitute in the expression for B1, okay, the magnetic field of wire 1, and we once again simplify. We see that these forces are exactly the same, right, which we would expect due to the symmetry in the problem, right? So the magnitude of the force on wire 1 is exactly equal to the magnitude of the force on wire 2. And, you know, think about what Newton's third law would tell you about that, right? We'll try to demonstrate this in the next slide here, okay, what this is going to look like. So at least you can believe that, okay, current carrying wires do exert a force on each other.
Here we have our two parallel conducting wires, and we've connected them to the power supply such that the currents will be in the same direction. And we would expect that when the currents are in the same direction, they should attract. Remember that the wire you see on your left sets up a magnetic field around it that interacts with the wire you see on your right, and vice versa. So the end result is that the magnetic field created by one wire, okay, will interact with the other wire, and that current in the other wire interacting with the magnetic field will experience a force. So both forces will be attractive in this case. Let's turn the power supply very quickly and see what happens. Attraction. We've now switched the leads in one of the wires connected to the power supply, so the currents in the wires should be in the opposite directions, in which case we now would expect that the wires, the magnetic force, should repel, so we should get repulsion. So let's try it out. Let's flip on the power supply, okay, and indeed the physics works, okay, repulsive force.